In this video, we're going to look at the Koch curve and ask ourselves the question, if we're using recursion to generate a fractal pattern, what if we want the parts of that fractal pattern to move or change or animate or do something after that pattern's been generated? If you go back and look at the previous two examples we made, it wouldn't be so easy to do that. The recursive function just kind of bloop, draws all that stuff to the screen and it's just there. We don't have access to all of those positions. But there's a way that we can do that. Let's first start though, let's use a why not? Let's use a different fractal this time, and we're going to use the Koch curve. So the Koch curve has some similarities to the Cantor set, which we just looked at. The Koch curve, which can be used to make nice little snowflake patterns incidentally, is we also start with a line. Start with a line. So here's our line. Now, what do? We also, the next step is divide the line into thirds. So the same thing, we divide it into thirds. This is just what we did with the Cantor set, but now, what do? We erase, boy, this looks really the same, erase the middle third. Okay, I get my eraser here, erase that middle third, and then the last thing that we do though, however, is connect middle section, there's probably a better way to write this, with an equilateral triangle. So this is the last step. What do I mean? Connect the middle section with an equilateral triangle? What does that mean? It means, right, we could imagine an equilateral triangle sitting there where each side is the same length of that third, but we're not going to use the bottom. So we're going to connect it like so. So I guess connect the middle section with the sides, with two sides of the equilateral triangle. So that's our production rule. We went from one line, and at the end, we got to this. And what do we have now? We have 4 lines. What do we do with each one of those? Erase the middle third, erase the middle third, erase the middle third, erase the middle third, and I didn't do this very well, but make an equilateral triangle, make an equilateral triangle, make an equilateral triangle, make an equilateral triangle. Hey, let's do that again. Erase all that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah, blah. We could do that over and over again. This is a fractal. You could figure out, you could go look at that Cantor set example, you could expand it a little bit and do a little more math, and you could have the Koch curve. But we want to do something slightly different. What if we now want all the pieces of that Koch curve to move? What if we want all of these line segments essentially to be objects? Objects that could have physics. After all, we spent all this time figuring out a lot of physics stuff. We might as well figure out a way that we could apply it to a fractal shape. Not all scenarios do you need this. Certainly if you're doing a print design and you just need a static fractal pattern, through some recursive algorithm, you could make it, but this is an important consideration that does come up in a lot of different scenarios. So how are we going to do this? And I call this, because I've come up with lots of fancy names, the Arraylist Technique. Okay, so what do we mean by this Arraylist Technique? What's the difference? Well, let's say for a moment that we had an array list. And we're back. That we had an array list. That's the other camera. I'm going to have to fix that. That we had an array list, and inside, and we have a line object. A line object maybe just has 2 p vectors, a start and an end. So we have this line object, and it has a start and an end. And we have this array list, and what do? Is that we put that line into that array list. We make a line object and we put it into the array list. The recursion isn't a function that calls itself. It's going to be an array list that iterates over itself. So this is the array list, we can say, at generation 0 in a way. At the very beginning, what do we start with? We start with one line object. And now we say, hey, in this array list, let's take this line object, use its start point and end point, and figure out what are all the points for the next line object. And then we have 1, 2, the array list suddenly has 4 line objects in it, and it's now at generation 1. Then it's going to have 16 line objects in it, if I did the math correctly. It's at generation 2. Whatever the state of the array list is, we're going to iterate over all of the elements and for each element in the array list, produce 4 new elements. And the way that I drew this, I'd like to draw it a slightly different way. Remember when we did, if you go back and look at the cellular automata videos, we had this idea of a generation. And we're going to do the same exact thing. We have an array list which is essentially current, and it might be represented by this singular line. And then we're going to have an array list which is next. And we're going to use that line to generate the next array list, which will have 4 line objects in it. And then that becomes the current one. And we could do it again and again and again. Okay, I hope this is somewhat clear. But I have no way of knowing other than my own sometimes inaccurate intuition. But let's take the next step forward and look at this in the actual code and see if we can understand it a little bit better. Okay. Darkness, sadness, light, happiness. Okay, I'm back. Camera was off. So first let me just run this, and we're going to see it in action. So here is the first line, right? And notice here, what do we have? We do have a Koch, I called it a Koch line, right? A Koch line object which has 2 p vectors, start and end. Okay? And now if I go back to the main tab, we can see, hey, what are we doing? We are making a Koch line first at 0, height minus 50, and then at width, height minus 50. We add that to the array list, and then, hey, there's one line. Let's display it. And there we go, just that one line. Now, notice also that there's a key press function right here, which calls a function called generate. So when I press a key, there you are, that's the camera. When I press a key, look, I generated the next generation. I took that one line and somehow turned it into 4. Then I took those lines and turned each of those into 4, again and again and again. And I could do this to infinity, but you can see there's a limit to the kind of resolution we have here and how much. But look at this interesting kind of quality that we've got already, this giant arrow. Whoa. Okay, so we can see that this works. We're getting the fractal pattern. We could imagine that there's some math involved in how do we take that one line and turn it into 4. But rather than look at the math, let's actually look at the guts of this generate function and see if we can understand what it's doing. So here is all that code. And I want to talk through it in a moment. But first of all, it looks a little bit like gobbledygook. So let's kind of clear up one aspect of it. Look, for every line, get points A, B, C, D, and E, and make a bunch of new lines. Let's see if we can make sense of that for a second. Right? If this was our original line, and this is what we're going to get, right? This is start, and this is end. And what do we need to make these 4 line segments? We need all of these points. So we need to calculate A, B, C, D, and E. And we can call this, I don't remember what I said in the code, A, B, C, D, and E. Okay, that's all I did. So we need to get all, how many points is this? 5 points. If we have start and end, how do we get all 5 points? And then we can make a new Koch line that's between A and B, and a new one that's between B and C, and a new one that's between C and D, and a new one that's between D and E, and all of those line objects should go into our array list. Look, that's exactly what's going on here. For every line, we know when we started there's just 1, but for every line, let's ask each line object, where's your A, B, C, D, and E points? Then let's make a line from A to B, a line from B to C, a line from C to D, and a line from D to E, and add those all to the array list next. Next is the new generation. Lines is the current generation. But once we make the next generation becomes the current generation, right? That's what we're drawing. We're drawing all the current lines. So when we start, current lines is 1 line. Then we generate, we make the next array list with 4 lines, and that becomes lines, and we see all 4 of those there. Okay, so this is the process. Again, it would be worth digging into the math behind getting all these points, but that's not what I'm concerned with right now. I'm concerned with this overall process, which I think I've kind of covered. Well, I was going to say one more thing about it, but now I've forgotten. Okay, so this is what's going on. So let's actually, okay, sorry. Let's just briefly pause and take a look at how those points are calculated, because I think it's something worth looking at. You can see that some of them are quite simple. right, point A is exactly the start. Point E is exactly the end. And if we go back into the code, we can say A and E are quite easy. Point B is not that hard either, right? Point B is just, hey, it's a point 1/3 of the length from the start. Sorry, 1/3 of the length from the start. That's point B. And we can see here, we're just reviewing our old vector math days. We make a we make a vector that goes from the start to the end. We divide it by 3, and we move from the start, and that's that location. So you can see C is a little bit harder. What do we have to do with C? If we're here, we can make this vector. We can rotate this vector 60 degrees and then move from here to there, and that's that point, right? The angles in an equilateral triangle, if you don't remember, if you make a triangle, each side being equal, each angle is 60 degrees. Maybe I didn't want to go over this math stuff, but I just kind of talking you through it very quickly. You can see that's what's going on. Start at the start, divide by 3, go to there, then rotate that vector by 60 degrees, and then go from there. So again, the part of this process of making a fractal pattern is kind of mapping out the shape and seeing if you can figure out how to turn that shape into vectors so that you can subdivide, move along, get to this point. That's what we're doing. But okay, so I just wanted to briefly point that out. Whoops. But back to this. So why did we go through all that trouble? After all I have on the screen is my static fractal shape. But we now have, if I go into this, if I zoom in, every single one of these line segments is an object. And I know its beginning point and its end point. I could grow flowers from there. I could suddenly put characters at all those points. I could have them all wiggle and move around. Let's try that. Right? What would it mean to add a function here, right? The Koch line has a start and an end. First of all, I could start adding physics. I could add velocity, I could add acceleration, I could add an apply force method, but we're not going to go that crazy. All we're going to do is we're going to add a function, I guess I'll do it towards the top, which is just called wiggle. And what I'll do is I'll say, hey, give me a random velocity, a random vector, which I'll consider a velocity, and then, hey, add that velocity to the start point. Right? So that's wiggling, and I'm only wiggling the start point. You know, you can wiggle the end point, it will probably be more interesting looking, but let's just, anytime I wiggle, I'm just moving that start point. And, okay, I can't resist. Let's get another random vector, and let's also wiggle, let's also move the end point. So what we're doing is we're making 2 random vectors and adjusting the start and end location. So now if I go back to the draw, and if I want to say, hey, when the mouse is pressed, let me also loop through and wiggle all of the lines. So right here, I'm just adding a little bit of code that anytime I click the mouse, whatever lines happen to be the array list, move them around. So I could run this sketch, and it's not doing anything different. It's exactly what it was before. And I could also run it, but I could also click the mouse, and look, this line is kind of moving it around. Once that line moves around, I could go a few more generations, and look, those lines can now move around. But I could continue doing the fractal, and those lines could move around. So we haven't completely lost the shape of the fractal, but it's gone a little bit awry. And now we have some weird randomness, and maybe I could wiggle it, but actually remember which object's endpoint is actually the start point of the other object, which would be super interesting. There's a great exercise for you to try. But this is the power of what we're doing. All these fractal shapes that we've created, if we make the parts, those broken parts that approximate the whole shape, if we make those objects in an array list, then we can start to apply things to them or know all the positions to generate things from those locations. There's lots of things we can do. All right, I think that's the end of this particular video. I've got 2 more things to look at. One is, what happens if we want to translate and rotate in the process of making this fractal shape? Kind of interesting. And also, I want to look at this concept of an L system, which is a recursive algorithm for generating sequences of characters that can be instructions for drawing. So those are the 2 other things we'll look at soon enough. Okay.